let's talk about functions. Functions are based on this idea in mathematics called a relation. And a relation in mathematics is a correspondence between two sets. Okay, those two sets in a college algebra class are the domain, usually the x values, we're talking about equations, and the range, usually the y values. Okay, you might also see input and output used, but most of the time you're going to see x and y or the words domain and range. But those are the sets that we're going to have corresponding in order to make a relation. Relations are sometimes written as a set of ordered pairs. That's always a good example of a relation. So 3, -2, 5, 6, -7, 8. And we could add more to that if we wanted to. But just the idea, we've got a set of ordered pairs where you have 3 x values and 3 y values. That relation is the correspondence between those x's and y values. Okay, so a relation is just a correspondence between the domain and the range. Where we get into functions, a function from x to y. That's how we deal with functions in college algebra. For the most part, we're going from x to y. So the input is x, the output is y. They can be done the other direction, but in a college algebra class, we generally go in this direction every time, okay? So from x into y, what it does is it associates each x with one y value. Okay. Kind of the shorthand way of remembering that is it doesn't repeat x values. The way I always tell my high school students is the way to remember this is if you want to function properly, don't repeat your x's. And they always think that's a good way to remember it. And so if you want to function properly, don't repeat your x's. A function doesn't repeat x values. Okay, so the first game we're going to play here is the famous, it's just slightly less famous than Wheel of Fortune, but it's still pretty famous, is the relation a function. We don't give away any spectacular prizes, but hopefully some easy answers here, okay? All we're going to do is we're going to look at a relation to decide if it's a function. There are several ways a relation could be written. One of the ways we've already seen, and that was a set of ordered pairs, like this set, 2, 3, -3, 5, 6, 4, and 8, -2. The only check we have to do to decide if that relation is a function is look to see if it repeats what? The x's. If any of the x's repeat, not a function. So do any of the x's repeat? 2, -3, 6, 8. All different, right? So there's no repeating, so that is a function. So the answer to that one is yes. Let's look at another one. -3, 7, 8, -1, -2, 7, 8, 0. So we're looking at this relation and trying to decide, is that a function or not? And if it's not, we're going to tell why. So what's the only test to see if something's a function? Does x repeat? Is there an x that repeats here? Yeah. Which one? The 8. So these 8's repeating here means that's not a function. And the reason would be repeated x value. Okay. So when we get a list of ordered pairs, we're just looking at the x values. If anybody repeats, then it's not a function. What about this 7 and 7 here? They repeat, but what kind of value is that? It's y value. Is it okay for y values to repeat? Yeah, it's quite okay for y values to repeat. We don't have to worry about those, just the x values. So listed ordered pairs, really easy to tell. You just look at them until that list gets really large, and then it's hard to tell. But you're not going to get a large list, especially from me. So let's look at another way of writing a relation, and that it's what it's called a mapping. And what they do is they have a couple of bubbles, and one bubble is the domain bubble, and one is the range bubble. Okay. They might have 3, 5, and 7, and then -2 and +6. And then they draw arrows from one bubble to the next to kind of mimic ordered pairs. So you might have 3, 6, 5, -2, and then they might have 7 going to -2 as well. So that's a mapping. And it's just another way of writing ordered pairs out of that. So what we're looking for here is this a function or not? So we're looking for what to repeat if it's not a function. If x is repeat, it's not a function. Where are the x's at in this problem? In the domain bubble or the range bubble? Domain. Domain is x. So do any of the x values have 2 arrows coming from them? No. So that would be yes, this is a function. So I'm just making up numbers here. 3, -5, 8 in the domain bubble. 7, -9, -10 in the range bubble. And let's just throw some arrows on there. Is that a function? No. Why? Yeah, that domain value of 3 the x value of 3 repeats. So that's why it's not a function. So we got a repeated x value. So mapping, it's the same thing as an ordered pair. It's just written differently. It's the only thing out of that. All right. Okay. Another way that a relation could be expressed would be as an equation. Y equals 3x minus 2. And if they give us an equation and we can get y by itself, one of the best things that we can do is graph that. Okay? And we'll do a rough graph by hand, and then I'll show you with the graphic calculator. I know some of you probably don't have that with you tonight, which is fine. I just want to, I'll put it on video on how to graph if you've never done that before. So if we're going to graph that by hand, we've got to remember something about this type of equation, that it's, anybody remember ever seeing that y equals mx plus b before? That's pretty familiar. The b is the y-intercept. That m is the slope of the line. So this equation is already in that form, so it's easy to graph. So I would go up to 2 on the y-axis, and then I'm just making my grid here. I would normally use graph paper, but because this is just one equation and we're just testing if it's a function or not, I can just kind of get a rough idea here. My y-intercept for this one would be at -2, and my slope would be up 3 over 1. So I'd count up 3 steps, 1, 2, 3, and then over 1. And I'd get that line that goes there. If I can get the graph drawn, then I can use the vertical line test. What the vertical line test does is it looks to see if any x's are repeated. So I would take a vertical line and I would place it anywhere on this graph. Is there anywhere that I could place a vertical line in which that vertical line would touch that graph in 2 places at the same time? Not on this one. Okay? So this passes the vertical line test, which means no x's repeat. So this would be a function because of that. Okay. And I'm just going to write passes the vertical line test. And I usually abbreviate that VLT, vertical line test. If I ever say that, VLT is a vertical line test. All right. Now, what if you've got an equation maybe like this? Y equals plus or minus the square root of x squared minus 4. This one's a little different. I want to show you a little bit about this particular graph. I'm going to show you with the graphing calculator a little bit about this graph. So let's first, I'm going to show you how to graph an equation with the graphing calculator. In order to be able to graph an equation with the graphing calculator, you got to have y by itself. So in that example E, we already had y by itself. So I'm going to graph that one first because it's a simpler problem. And so to graph, you're going to press the y equals button, which is the top left button that the calculator has. And then it takes you to this page. And then you're going to type in the equation. Our equation was 3x minus 2. So I'm going to type in 3. And then to get the x up here right beside the green button, the alpha button is the variable button. And if we hit that, we get an x. You don't have to hit alpha and then the store button to get the x. You can just hit that. It's a shortcut button. And then minus 2. If I do that and hit graph, there's that same line that I just drew by hand. Okay, so that's the nicety of the graphing calculators. I'm usually not going to ask you to graph much by hand. I'm going to ask you something about that graph, which if you can get the graph with the graphing calculator, you can get that information. Okay. Now I'm going to go back to y equals, and I'm going to graph our more difficult problem from example F. And it has this plus or minus in the front of it. So what that means is we've got really 2 equations that we have to graph. One of them is the positive side of the square root of x squared minus 4, and one is the negative side of that. Okay, that's what that plus or minus in the front means. Okay, so when I go to graph that with the graphing calculator, I've got to put in 2 different equations for that. So I'm going to put the positive side in y1. So to get the square root button, you hit second, and then right there in blue above the x squared is the square root. So it gives me a square root symbol, and I'm typing x squared minus 4. Okay. And then I'm going to go down to y2, and I'm going to put the negative side of that. So I'm going to hit negative, which is down here below beside the enter button. That's a negative. If you hit a minus sign right there, it's going to give you an error. So be careful of that. Make sure you're using the negative sign. And then the square root button, and the same thing, x squared minus 4. And when I graph that, it loses a little bit here in the middle. The resolution gets real kind of too much. If you've got a black and white one, it really, the resolution's not nearly as good as the color ones are. But what we got to think about is this is one graph. We had to write it in there as 2, but it's one graph. Does that pass the vertical line test? If I take a vertical line and draw it right down through here, how many places does it hit? 2. That's all it takes. Just one place where you can hit it twice and it fails. So this would not be a function. Okay? This is not a function. Fails the vertical line test. So a lot of times, if you're getting an equation and graphing it and then doing the vertical line test is the quickest and best way to determine if it's a function or not. But you got to get y by itself to be able to graph it. So that sometimes that takes a little algebra to make happen. But usually in chapter 3, it's not much. Okay, so determining if something is a function, we're looking for x's not to repeat. X's cannot repeat if it's a function. If you have an equation or a graph, vertical line test is what you want to use to determine if the x's repeat or not. Okay. Next kind of subtopic in the same section is function notation. All right. Function notation looks like this. F of x is how that's said. It's the same thing as y. That's how you read that. F of x is how that's it's not f times x, it's f of x when you're talking about function notation. And one of the things that we might have to do is find the function value f of -5, 4, and then they give you this function f of x equals 3x plus 5. So they give us this function f of x is equal to 3x plus 5. It's in function notation, so we already know it's a function. We don't have to test it with the vertical line test because they wrote it with that notation. We're saying, oh, well, you already know it's a function, so we don't have to do anything with that. So what we're going to do is take that -5, and everywhere there's an x in that problem, we're going to replace x. Okay. 3 times -5 is -15 plus 5. So f of -5 is equal to -10. That's the function value. What that really creates is an ordered pair where -5 is the x value and -10 is the y value. That's what function notation is. It's a more descriptive way of getting an ordered pair from an equation. That's what function notation really does for us out of that. So we're anywhere there's an x, replace it with the number inside and work it out. That's function value. Let's look at another one. F of x equals 2x squared minus 3x. And we want to find, let's find f of 2a. So throwing a variable in there, get our algebra skills cranked up. Things we need to be able to do here. So if we're going to find f of 2a, where are we putting 2a? In the place of x. In every spot that there's an x in that problem, we're going to put a 2a. So it's 2 parentheses 2a squared minus 3 is 2a. Just plugging those in, and then we're going to work them out using order of operations, parentheses, exponents, multiplication, division, left to right, addition, subtraction, left to right. So there's a parentheses with some exponents involved. So when we square 2a, what does that mean? Yeah, 2a times 2a times itself. You know, so that'd be 4a squared. And then I'm going to go ahead and do the multiplication on the end here. 3 times 2a, 6a. And then finish it off, be 8a squared minus 6a. Don't get a nice number there, but it is function value for a given x out of that. Doesn't look pretty, but it is part of it, okay? Sometimes they can throw this at us. Same function, f of x equals 2x squared minus 3x, and they want us to find f of x plus 2. So they even use the same variable, but different function value. So what are we replacing x with? Yeah, x plus 2. Excuse me. All right. When I square x plus 2 right here, what does that give me? Close. What does it mean to square x plus 2? It means x plus 2 times x plus 2, right? So it'd be x times x is x squared. And then, y'all hear the word FOIL? I remember hearing that maybe in a math class somewhere. I don't ever teach it as FOIL, but most people that I've taught here have heard FOIL. I just call it distributive property because it's the same thing. So I'm distributing x to both of them. So that's x squared plus 2x. And then I distribute the 2 to both of them. 2 times x is another 2x, and then 2 times 2 is 4. So there's a middle term that's in there that happens to give us 2 times x squared plus 4x plus 4. And then this other one I'm distributing negative 3, so that's negative 6x minus, or excuse me, negative 3x minus 6. And then I've got to do one more distributive property here to get closer to getting the answer. Now, what gets put together? Yeah, the plain numbers and the things that have a plain x on them. The 2x squared doesn't have anybody else that's like him, so or her. I'm not sure what a 2x squared is. If it's a boy or a girl, but 2x squared, and then we have 8x and negative 3x that go together to make positive 5x. Then we have an 8 and a negative 6, which would be plus 2. This would be our function value. I could draw a box for f of x plus 2. So a little bit of algebra there. We do that. You may not have done this in 8th grade math, but that's something our 8th graders do now. It's crazy. I don't think I did that until I was a sophomore in high school. So it's kind of crazy what we're asking them to do at such a young age now. That's is what it is. All right, now those are when you're just plugging something in for x. Sometimes they want you to do something to the function, and they'll use the function notation to help us get there. And so what they might do would be something like this. I don't know what letter is where you have the same. Let's just use the same function because it really doesn't matter what function we use. Let's be boring and use that. And they ask us to find 3 f of x. So What does it mean when you push a number right up against something? What operation are you doing? So like if I had 3x there, that means what with the 3 and the x? They're multiplying. So that's the same thing here. The function notation is we're taking 3 times the whole function is all we're doing there. So 3 f of x just means take 3 and multiply it to the entire function. That's going to get us 6x squared minus 9x. A real simple idea, but if you don't know what they're asking for, it just looks like 3fx is there. What's that mean? So nothing difficult there. Where a lot of folks I see a lot of mistakes in this particular section is when you change that sign in the front. So maybe you got the same function, f of x equals 2x squared minus 3x, and they just want us to find something. It seems so simple, but they write it and we lose it. Negative f of x. What does that even do? Changes the sign of the whole equation. That's exactly all that it does. So that would be negative 2x squared plus 3x. That's all that it does. It's one of the easiest things, but it's like one of those things. It's so easy that you mess it up. Kind of ideas out of that. So I always kind of try to make sure that we show that. Now, where that gets confusing sometimes also is that if we've got the same function, 2x squared minus 3x, I mean, I'll get tired of that one, but we're almost done with it. So when they do this, find f of negative x. So they can throw that in there and kind of mess this up a little bit. So f of negative x means what? Yeah, replace every x with a negative x. So that's 2 parentheses negative x squared minus 3 parentheses negative x. And then just work that out. So I treat that as a negative 1x, if that makes it make more sense. So that it's a lot like one of the previous examples we did. So when I square negative 1x, what happens when I square that? Yeah, it always, anytime you square something, it's going to turn back to positive. So that's just going to be positive 2x squared. And then the minus 3 times the negative x becomes positive 3x. And there's our f of negative x. So it doesn't necessarily change the entire problem like example K did, but it does change some of it. Now, I want to show you how to find a function value using a graphing calculator for like, anytime you need to find a function value. So using the TI-84, let's say we had f of x is equal to 2x squared minus 3x, and they wanted us to find f of any number really, but what if they were mean to us and they threw a fraction in there like 3 11ths, something weird like that. With the graphing calculator, that's a little easier to do. There's a couple different ways to do it. One way would be just on the regular home screen, the calculator screen. If you're in the graph, to get back there, you can hit clear and it'll just take you back there, or you can hit second and then the mode button will always take you back here no matter where you're at on the calculator. So second mode is always get me back home buttons for the graphic calculator. So one way is just type it in directly, 2 parentheses 3 divided by 11, and then squared minus 3 parentheses 3 divided by 11. And that gets you this. If I want to change that to a fraction answer, because they gave me a fraction to begin with, and the answer choices are all fractions, and that's a fraction. It's just kind of hidden. The way to do that is hit math and then enter, and it will change any decimal answer back to a fraction answer. So negative 81 over 121. That's one way to do it with a calculator. Another way to do that is to actually store that value that they want you to plug in as x. So you could do like 3 divided by 11, and then hit this button down here in the left, right beside the number 1 is the STO. That's short for store. And then you can tell it what letter you want to store it as. I want to store it as x, and it just converts it to a decimal, but it remembers that decimal repeats forever. And then you can type in the actual function, 2x squared minus 3x, and we should end up with the same. Yeah, it's the same answer that we got there. So there's a way to do it. If you're going to have to use the same x value over and over for several problems, then that's probably the way that I would do it. But otherwise, if it's just one individual problem, I just type it in using that. If you're more comfortable with seeing it as a fraction, the TI-84, one of its nice things is that if you hit alpha and then the y equals button, you get these nice little pre-made fraction things. So if you needed 3 over 11, you could make it look pretty. That's about the only real nice part of that, is it looks better. But 3 divided by 11 is the exact same thing as far as the calculator is concerned. It's just a computer. It doesn't really care what it looks like. It just wants answers. Okay? All right. Continuing section 1, believe it or not. All right, so we're still in section 1. Section 1 is pretty heavy. Got a lot of stuff in it. Because it's talking about functions, we need to talk about the domain of a function. The domain of a function are all the x values that quote unquote work for the function. Okay. And what I mean by work are numbers that don't, the x values that don't cause red flags. Okay. And so by default, domain starts with all real numbers. Okay. Negative infinity to positive infinity. This is the interval notation. So we're going to be working back and forth between set notation and interval notation. Interval notation has the parentheses, the brackets, the infinity symbols, and all that stuff. Set notation is like inequalities, like x is less than 5 or something like that. Okay, so by default, everybody starts with every real number in the world, from negative infinity to positive infinity. What happens with a function is we get these red flags that can come up. So if one of the red flags that can come up is that there are x's in the denominator. That's a definite red flag. And if there are x's in the denominator, what that can create is division by 0 is what could happen there. Okay, that's why that's a red flag, is because 0 is the only number in the world we cannot divide by. Because if I give you a candy bar and say, break that into 0 pieces, it's impossible to do because you've got one candy bar. If I don't break it at all, I've still got one piece, right? I can't break it into 0 pieces. But if I give it to you and I say, break that into 2 pieces, that's easy. You break it in half. You got it. Or if I say, break it into 3 pieces, 6 pieces, so we could all share it. That's easy to do. But 0 pieces is impossible. So division by 0 is the reason that that's a red flag. And we're going to see some examples here of when that occurs. What do we do to find those X values that don't work? All right. The other red flag, and I say the other because there's only two that you got to know. Just two red flags. The other red flag is that there are square roots in the problem with x's. Okay. Square roots, we can only take square roots of positive numbers. When we're talking about domain, we're talking about all of this relates back to graphing things on the coordinate plane. It's what it all relates back to. And the x-axis on the coordinate plane is only real numbers. If you remember from your Algebra 1 or Algebra 2 course, if you took the square root of a -1, y'all remember that was I? Y'all remember seeing that sometime in your life? Well, i's don't exist when we're talking about domain. Domain is only dealing with the x-axis on a graph. There are no i's on that. So what we've got to take care of there so we can talk about domain is we can only have positive square roots with an x inside of it. So that's the other red flag that could happen. So only two red flags exist as far as domain goes. One of those is that there's an x in the denominator or something with an x in it in the denominator. The other red flag is that you have an x or something that has an x in it underneath the square root. So we need to find out, well, when is that stuff under the square root positive? Because if it's negative, then the I comes in, and we don't need any of that when we're talking about domain. We don't worry about the I's when we're dealing with that. So what we're going to do is we're going to look at some functions, and we're going to decide if they're red flags. If there are no red flags, we're going to go to the default domain. All real numbers, x is from -infinity to positive infinity. That's domain if there are no red flags. If there's red flags, then we got work to do, and then that's going to change. Okay, so if there are no red flags, we go to the default domain, all real numbers, or -infinity to positive infinity. So example N, find the domain. All right, here's our function, f of x equals x squared plus x minus 7. So we look at this function. They tell us it's a function, so we know it passes the vertical line test. We know it does all these wonderful things, and it graphs on the coordinate plane and wonderful stuff. But if it asks us just to find the domain, all we've got to do is look for red flags. So the red flags we look for are x's in the denominator. Do I even see any fractions here? So that one's out. That red flag can't exist. Do I see any square roots? No, I got a squared, but that's not a square root. So neither of those red flags can exist in this particular function because they're just not there. So the domain of this one would be from -infinity to positive infinity. Or in set notation, curly brace, x, then this straight up and down bar, and the way that's read is all x's such that x is a real number. That's a way of writing it in set notation. I like interval notation because it's shorter usually, and a little bit more descriptive about what's going on. So that means no matter what x you pick, it works in this problem as long as it's a real number. No i's involved, but real numbers. Okay. So g of x equals 5x over x plus 3. Again, we're finding domain. That's all we're doing here. Just find the domain of this function. Now, red flags that could exist. X is in the denominator. Is there a denominator to this problem? Yeah, we got a fraction that's got an x plus 3 in it. There's an x in the denominator. There's the red flag. We got a red flag right there. Now, what do we do with that? Well, what's the only number that we're not allowed to divide by? 0. So we need to know when is the denominator equal to 0. That's what we need to know. Okay? So we take x plus 3 and set it equal to 0. So we're taking that denominator and setting it equal to 0. And we're going to solve that equation. Subtract 3. That denominator is 0 when x is negative 3. Okay? What that tells us is negative 3 is an excluded value. So the domain are all x's as long as they're not negative 3. There's the set notation for it. The way interval notation works for that is you take and you think, okay, I'm taking the default domain, starts at negative infinity. So I'm walking along from negative infinity. Let's pretend this corner is negative infinity. So I'm over here at negative infinity. I'm walking along, going just fine, and then I come to negative 3. This function, negative 3, does not work. So I've got to hop over it. Okay? So to hop over it, notation-wise, so we're starting at negative infinity. We walk all the way to negative 3, and then we're going to skip it. To skip a number, you put a parenthesis, then a U, another parenthesis, and put the same number, and then keep walking. Okay? Once we hop over negative 3, so we walk from negative infinity all the way over here. I'm at negative infinity. I'm walking along, and this plug-in is negative 3. So that right there, I've got the negative 3. I've got to hop over that, and then I'm going to keep walking until I find another place that there might be something wrong. Is there any other place that something's wrong? No. So what goes after negative 3? Positive infinity, because I'm going to keep going. I don't have any other problems in this particular. So there's the interval notation for skipping negative 3. So anytime you got to skip a number, you're going to use parentheses with a U in between. Okay? Sometimes we got to skip more than one number. We'll get to some like that in a minute. Okay. H of x equals 12 over x squared minus 16. Do we have a red flag with this one? Yeah, there's an x in the denominator. How do I work it? How do I find out what messes that up? Set the denominator equal to 0. And we've got to solve that. Several different ways to solve this one. I think the easiest way is just to add 16. And what's the opposite of squaring? Take the square root. The only thing we have to be careful of is what numbers can I square and get positive 16? 4, but also negative 4 can be squared too, because negative 4 times negative 4 gets you positive 16 as well. So there's a plus or minus that could go in there. So x, our numbers that mess this up are positive and negative 4. Both of those, if I plug them in for x, would give me a 0 in the denominator. And I can't divide by that, so I've got to take care of those. So the domain, if we're in set notation, x such that x, it can't be plus or minus 4. That's like the shorthand way of writing that. Okay. The interval notation for that, where do we start with interval notation? Negative infinity. What's the next number we're going to encounter that's a problem? Negative 4 comes first. We're going to skip it. So parentheses u, parentheses negative 4. And then we're going to keep walking until we get to where? Positive 4. And we got to skip it. And then after positive 4, we don't have any more problems, so we can go on to infinity. So there's our domain in both different forms for that particular problem. All right. X in the denominator, you're going to set that denominator equal to 0 and get the numbers that X cannot be. F of X equals the square root of 2X minus 6. Is there a red flag here? Got a square root with an X inside of it. That's a red flag. So the way we're going to take care of that is we're going to take whatever's underneath the square root, 2X minus 6, and we're going to set it greater than or equal to 0. Because I can take the square root of 0, that's why I've got an equal to mark. If I'm greater than 0, what kind of number am I? What kind of numbers are bigger than 0? All positive numbers, right? And remember, that's the only kind of numbers that we can take a good square root of. Anything that's negative is going to get that I involved. We don't need that part of it. So we're going to solve this inequality. Plus 6, so that'd be 2X is greater than or equal to 6. Divide by 2. X is greater than or equal to 3. Now, the difference with the square roots is this means these are the ones that work. When we were doing the denominator problems, those were the ones that didn't work. So this is actually the domain that we want. So our domain all x's, as long as x is greater than or equal to 3. That's the set notation of that. The interval notation is just as short and just as easy. It goes from 3 to positive infinity. The equal to mark, instead of putting a parenthesis on the 3, I'm going to put a square bracket. That means 3 is included. The square bracket means equal to. So 3 is included in that answer. So that's the domain for that particular problem. Okay. So whatever's underneath the square root, set it greater than or equal to 0 and solve. And that's going to get you what works for that problem, the actual domain. Let's do this one. G of x. Square root of 8 minus 2x, and then plus 7 on the outside. Is there a red flag for this one? Okay. Right there is that red flag. What about the plus 7 on the outside? Does it cause a problem? No. So the only part we've got to worry about is that stuff that's on the inside of the square root. That's the only thing you got to worry about. So we're going to take that x minus, or that 8 minus 2x, and put it greater than or equal to 0. The plus 7 really has nothing to do with it. And we're going to solve that. Subtract 8. Divide by negative 2. Does anybody remember the rules when you divide by a negative with inequalities? Yeah, it flips the symbol, and then the sign, as far as the other side here, it's going to be positive, but it doesn't necessarily mean that you have to worry about that. But it's, if you multiply or divide by a negative, you got to flip this symbol and then work out the problem the way. But we're going to flip it to less than or equal to positive 4 for this. This is negative 8 divided by negative 2. Okay, so that tells us that the only things that work are x's that are less than 4. So our domain from negative infinity up to 4. And we're including 4. So there's the interval for it. The set notation is just, you copy the inequality. I mean, it takes no brains to do set notation. Copy what you got. So negative infinity is definitely less than 4, and it goes all the way up to 4, and it includes it because we had an equal to mark. All right, let's do one complicated one, and then we are finished with section 1. Okay? And then the next 2 sections are not nearly as heavy, I don't think. All right. RS. K of x equals x minus 7 over the square root of 2x plus 10. This one's a little tougher. Where's the red flag? All right, so there's an x in the denominator, and it's also inside of a square root, okay? So a double red flag on that one. All right, so that tells us, okay, well, if it's in the denominator, what can it not be? 0. It can't be equal to 0. So when we set up our inequality for 2x plus 10, do we put greater than or equal to 0? What do we put? Just greater than 0, because we can't be 0, right? We cannot have 0 in the denominator. So we take the equal to off because it was in the denominator. This is one of those weird special cases that comes up like once out of 100 problems. But it's just, to me, it's interesting. So subtract 10. 2x is greater than negative 10. Divided by 2. Do I flip my symbol on this one? No, I divided by a positive 2, not a negative. So if x is greater than negative 5, and then that would be, what is that as a interval notation? What's the smallest number it could be? Negative 5. Do we put a bracket or a parenthesis? Parenthesis, because it's no equal to mark, right? If we had the equal to mark, it's a bracket. So no equal to mark, so it's a parenthesis, and then it goes up from there toward positive infinity. So there's the interval notation for that one. Yes, ma'am. That's correct. Bracket is with the equal to mark on the inequality. Parenthesis, there's no equal to mark. That's what happened. All right. If you do the textbook, I'm just going to write some suggested problems from that section that would be good to look at. So if you want to look at those, you can. That definitely would be helpful in prepping for the quizzes on Canvas as well. So, all right. All right, let's pull up my section. I want to copy this. Okay. Oh, all right, section 3.2, the graph of a function. I'm going to try to get that. That's pretty close. All right. So kind of try to sketch yourself that particular graph. I picked those weird numbers on purpose. That way you have to look at them. It makes us really look at the equation. Trying to sketch that. Main thing is get the ordered pairs. You know, this is the x-axis here, the solid line. This is the y-axis. Get these ordered pairs. These things here are pi. And a whole bunch of digits after that. So get those ordered pairs. That's the main thing out of that. So copy that down. And we're gonna. It's not so much the title of the section is the graph on function. Not so much about being able to graph a function, but actually answering questions about the graph that we're given. So the idea is to look at a particular graph that may be drawn, and we may not have an equation for it. We just have a graph. Like in this case, we don't have an equation for this graph that's given to us. There's one that exists, but we just have the graph and some information about the graph kind of given to us. And we'll call this example A. And we're going to answer several questions about this same picture. So we're going to be bouncing back and forth to it. Matter of fact, 1, 2, 3, 4, 5, 6, 7 questions about that particular graph. And then we'll talk about an equation that goes and kind of build some things up off its graph without even graphing. I'm just going to start over here on the right, writing some questions that we want to answer. We don't have room for 4 right there, so we'll just get those 3 right there while we're still looking at the graphs. All right, so the first question about this particular graph is, what is f of 0? So when we look at that graph, what does that even mean? This goes back to section 1, talking about function notation. What does the 0 represent? X. So if the x value is 0, what does f of 0 represent? It represents the y value that goes with it. What's the y value that goes with the 0 x value? We go for a graph. Okay, 0 for x would have to be here. And the y value that goes with that. Very simple idea, but getting it from a graph without an equation is sometimes foreign to us. So the answer to that would be 4, because we're going over here to where x is 0 and then finding that y value that goes with it. That's all we're finding there. Okay. This one's a little tougher. The domain. Because we just did a whole thing about domain, but we had equations to deal with. We don't have an equation, we got a graph. What's domain for this particular graph? What does domain deal with? X's or Y's? X's. So domain is going to be left to right. how far does this graph go with x values from left to right? So the way you do that is you read it from left to right. So I'm reading it along here. What's the first x value that I come in contact with that's on the graph? 0. And I keep going, and I look for places where x is left out. If there's something left out, there will be an empty circle, like a hollow circle. They'll draw it like, they might do it like this. They might put an open circle right there. That open circle would mean that that x value is left out. Okay, there aren't any of those here. So I follow this from 0, and I keep going. There are no hollow circles, no hollow circles. The last x value that I'm given here is 4 pi. It's a filled-in circle. So I'm going to count it too. So I'm going to put a bracket on both of those because they're both filled-in circles. If one of those was an empty circle, like a hollow circle, then that would be a parenthesis on it. Domain is x's, range is what? Y's. So range, we're going to read bottom to top. Okay? So if I'm reading bottom from bottom to top, what's the lowest y value that I come in contact with? -4. Both of these have to have a -4. It doesn't matter if they're the same, so just pick, just one of them. And then what's the highest y value that I have? 4. Are there any empty circles in between? No. So that means all of the y values from -4 all the way up to +4 are used. So our range is from -4 to +4. And brackets on those because those are filled in dots. If they're empty circles, it's parenthesis. Okay, easy, not too bad. I'm gonna have to flip back and forth here because it's just not room to do this on. Well, we'll do them for you. Let's talk about the intercepts. When I say intercepts, what do I mean? We're what? Explain a little bit more. Okay, I thought that's what you meant. I just want to make sure that that's what you're saying. Where the red line is crossing the x-axis, those are what kind of intercepts? X-intercepts. What other kind of intercepts exist? Y-intercepts. So when it says intercepts, they're saying any kind of intercept. So y-intercept, what would the y-intercept for this graph be? Be 0, 4, right? That ordered pair. What are the x-intercepts? Well, there's one right there. Pi over 2, 0. There's one right there. 3 pi over 2, 0. There's one right there. 5 pi over 2, 0. And then there's one more. 7 pi over 2, 0. So we have x-intercepts, 1, 2, 3, 4 of them. It's crossing the x-axis at 1, 2, 3, 4 spots. We have one y-intercept. It's not crossing the y-axis there, but it's touching it there. So that's an intercept. It intersects the y-axis at 0, 4. Doesn't carry on through it, but it does intersect it. Okay, so if it says intercepts, they're talking about all intercepts, x's and y-intercepts. So don't forget the y-intercepts. So because in algebra classes, we tend to focus more on the x-intercepts when you're doing stuff in that form. So don't forget the y-intercepts exist too. All right. That purple dotted line is important for this next one. How many times would y equals -2 intersect the graph? So we're looking y equals -2. If y equals a number, then it's a horizontal line. Add that number on the y-axis. So what I've drawn here, this is 0, there's -1, here's -2. So that's y equals -2. That's what that line is. Y equals -2. And how many times does that line hit the red line? 4. Didn't ask where, it just said how many times. Okay? So we don't worry about what numbers they are. We could estimate, but it'd be tough. But it just asks how many times. We just say 4 times. And that's it. You know, it's an easy question. All right, here's a tough one. And a couple of pretty easy ones there. This one's a little harder. It asks us where is the function, our graph. I say f of x, I'm talking about the red line. Where is it greater than 0? Greater than 0. Okay. What does f of x represent? You just say, what does f of x represent? F of x is another way of saying what? Y. It's y values. It wants to know where on this graph are the y values greater than 0. Now, doesn't that make a little bit more sense than f of x greater than 0? So, where are the y values greater than 0 on any graph? Think about, here's the x-axis. What are all the y values on the x-axis? They're all 0, right? So if the y values are supposed to be greater than 0, will they be above the x-axis or below? Above it. So if it asks for where's the f of x greater than 0, we're looking for where are these y values above that. And there's pieces of it. There's from here to here, here to here, and then from here to here. So we've got to get those pieces and tell what pieces that is. When we're talking about functions and graphs, they ask us about the y value. When is it greater than 0? But the way we report that is with x values, because that tells us where we're at on the graph. Okay? So the x values here, the first x value that's above, if we're reading it left and right, that's got a y value that's greater than 0 is 0, right? So from 0 till we get here, what's the x value there? Pi over 2. So that interval, that little piece, is from 0 to pi over 2. Which one is included and which one is not? Why? The y value for 0 is positive 4, and that's definitely greater than 0. So that one is included. What about this one? There you go. It is 0. It's not greater than 0. It's equal to it. So we don't have an equal to mark. So that's going to be a bracket on the 0 and a parenthesis on the pi over 2. Okay. Where's the next interval that the y values are greater than 0? 3 pi over 2? Is it included or not? Not. Okay. So we follow it from left to right from there. So it's y values are still positive, y values are greater than 0, y values are greater than 0. Stops right there, right? So from 3 pi over 2 to 5 pi over 2. Parentheses on both of those because if it's equal to 0, it's not greater than 0. Then we go back to the graph, we look at that. Okay, well, from 5 pi over 2 all the way to 7 pi over 2, the red line is below the x-axis, so that's definitely less than 0, not greater than 0. But at 7 pi over 2, it equals 0 again, and then it goes positive until we get to where? 4 pi, and it stops. So from 7 pi over 2 to 4 pi, and do we put a parenthesis or a bracket on 4 pi? Why? It's greater than 0, okay? All right. I said there were 7 questions. This is the 7th one. Where is f of x equal to negative 4? Where is f of x equal to negative 4? What's that mean? Where is y equal to negative 4? How many places does that happen? Twice. Right here, right here. Just list those x values. Pi and 3 pi. If you wrote it like this, x equals pi and x equals 3 pi, that's fine too. Okay? Just a list of the x values that's happening at. That's fine with me. Okay? Just making it clear. Okay? So there we're given a graph and asked to do some stuff with it that deals with domain and the fact that it's a function and finding some information through a graph. Let's look at an equation, and we can find a lot of the same information without even looking at the graph. Okay? Example B. Say we had f of x equals x plus 1 over x plus 2. First question directly relates to what we did in section 1. What's the domain of that function? And how do we find it? Is there a red flag that comes up? Set that denominator equal to 0. So x plus 2 equals 0, and that'd be negative 2. So that tells us that the domain is x, as long as x is not negative. Interval notation, that would be from negative infinity up to negative 2. Skip it. Go to positive infinity. So there's the domain of that function without even having the graph. We can get that domain just based on the equation. Always can get that. Okay. The next question is 1/1/2 on the graph of f of x. What? We don't have a graph. How can I tell if that point's on the graph if I don't have a graph? What's the 1 represent? Okay, the 1/2. Why? If x is 1, then y should be 1/2 if it's on the graph, right? Can I figure out what f of 1 from the equation? I can just go, oh, f of 1 just means take 1 and plug it in and work that out. So that's 2 over 3. But that's not 1/2. So what does that mean about the point 1/1/2? Is it on the graph of f of x? If these two don't match when I plug 1 in? Can't be. If they do match, then yes, it is. Since they don't match, that means, oh, when I plug 1 in for x, I get 2/3. Remember, x's can't repeat themselves if it's a function, right? So the only thing I can get when I plug 1 in is 2/3. I can't get 1/2 ever. So this is not on the graph. Another way to do that with the graphing calculator, you can actually get the graph. So I'm going to graph that one. I'm going to go to Y1. I've cleared before. And the way I want to graph that, I can hit alpha number 1 to get a fraction put in there. And I'm going to type in x plus 1 on top, and on bottom I'll put x plus 2. I'm going to hit graph. That's a funky looking graph. It really doesn't matter what the graph looks like. The thing is we want to check that ordered pair. The ordered pair we had was 1, 1/2. To check the x value, you can get the calculator to crank that out and look at it on the graph. If I hit trace and then type the x value I want to check, I want to check 1. And then I tell it enter. Look what it gave you here. Y is 2/3. Same thing I got when I plugged it in. Took me about the same amount of time to type it in as it did to work it. But I get 2/3, which is not 1/2. So that tells me that 1, 1/2 is not part of the graph. That 1 2/3 is, but not 1 1/2. Okay. Third question. Same function. Where is f of x equal to 2? That's a little tougher question. Because they're wanting to know where is what equal to? Y equal to. If they said where's y when x is 2, that's an easy question. This is a tougher question because we can't go to our calculator and type in the y value and get the x value that goes with it. But we can solve an equation here with that. So what we can do with algebra is take x plus 1 over x plus 2 and set it equal to 2. This looks like a really hard problem, but it's not. I can rewrite 2 as a fraction, make it 2 over 1. Y'all remember doing proportions, maybe in an algebra 1 class? How do you solve that? Yeah, cross multiply. Diagonal, diagonal. Set them equal to each other. 2 times x plus 2. So I'm just showing an extra step here you probably wouldn't show. You would probably go ahead and do this math and get 2x plus 4 equals x plus 1. And solve that problem. Subtract x and subtract 4. Be x equals -3. That's where x is equal to 2, or where y is equal to 2 at the point -3 and +2. I can check that with my graph on my calculator. All I've got to do is I've already got the graph drawn. If I hit trace and then type in -3, I should get 2 as my y value. Boom, I got it right. That tells me I got it right. All right. Next question. Last one of this section. Number 4, find the intercepts. All right. Finding the intercepts. Algebraically, so without the graph. What kind of intercepts do we have? X-intercepts and y-intercepts. Y-intercepts are the easiest to find because how do you find a y-intercept for any equation? You plug in what for x? Think back to our first example, that picture where we talked about the y-intercept for it. What was the x value when it crossed the y-axis? 0. So to find a y-intercept for any equation, you plug a 0 in for x. 0 plus 1, 0 plus 2. That'd be 1/2. So the y-intercept is at 0, 1/2. Y-intercepts are always the easiest. X-intercepts are not always easy. Okay? So if I'm going to find an x-intercept, I'm going to take the equation and I'm going to replace f of x with 0. I'm going to set the whole equation equal to 0. Not just the denominator, not just the numerator. Technically, it ends up being the numerator anyway. Because if I wanted to write 0 as a fraction, put it over 1 the same way that I did when I wanted to know when it was equal to 2. I set it equal to 0, and I cross multiply the same way. The beautiful part is, what's x plus 2 times 0? 0. What's anything times 0 just gives me 0 back, right? So that simplifies it to where it's just 1 times x plus 1 is x plus 1. Subtract 1, x equals -1. So the y-intercept is 0, 1/2. The x-intercept is -1, 0. That's the only intercepts I have. If I look at the graph of that, both of those are happening right here. Here's the -1, 0. Here's that 0, 1/2 that's happening. We can see them crossing. So you can get an estimate of whether that's right or not. Okay. So for this particular section, if you got the textbook, some problems that you could look at would be on page 224 through 47. I always just say the odd ones. The reason I do that is because your back of your book has the odd problems in it. So you can check, make sure you're doing them correctly. And if you're not, and you need help, one of the best things that you've got is a smartphone hanging around. Take a picture of what you've done to work on the problem and send that to me. Email it to me through Canvas. There's a Canvas app on your phone. Makes it really easy to do that with, because you can just native to the app, get the camera, take a picture of it. It sends it right to me. And a lot of times I can just look at your work and say, hey, you missed a sign on step 2, and then you get it, and it's great. So, all right, one more section and we're done. This one a little longer than section 2, but not crazy long. It's still a good bit of information in it, though. Let's see if we can make our way through this one. Oops. Keyboard up. All right. Still dealing with functions. All of chapter 3 is about functions. 3.3 is properties of functions. When we're dealing with functions, one of the things that we want to decide or want to be able to decide in the college algebra class is if it's an odd or even function. And there's a test for that. Okay? The test is to plug in -x okay, find f of -x. That's the test. Okay. The results, if f of -x equals f of x, then f of x is even. What that means, if you plug in a -x and work it out, and it turns back into the exact same problem you started with, it's exactly the same as the original, then it's an even function. Okay. And the way I think about that is, no matter what somebody that's kind of even keel, my dad is a good example of somebody who's pretty even. Seems like no matter what happens to him, he comes back the same as he was before. It's real steady. So if you plug in a -x and it comes back the same as it was before, it's even. Okay. If you plug in a -x and it comes back where everything changes signs, then f of x is odd. Anything else, then it's neither. Okay. There are there are odd functions, there are even functions, and there are tons of functions that are neither. Okay? So coming back exactly the same is even. Coming back completely the opposite, so everybody changes signs, that's odd. Anything in between is a neither problem. Okay? All right. Graphically, so we're going to do some tests with this, but with a graph, the graphic rules, which are a little more difficult to see than the algebraic rules. Even functions are symmetric with respect to the y-axis. Odd functions are symmetric with respect to the origin. All right, what's it mean to be symmetric? Something has symmetry, that means it's the same on both sides. So theoretically, my hands are symmetric, they match up, right? So if it's symmetric with the y-axis is the vertical. So if it's an even function, I should be able to fold the graph across the y-axis and match up perfectly. That's an even function. Okay? An odd function is a little tougher because it's respect to the origin. What that means is I can fold it across the y-axis and then fold it again across the x-axis, and then it should match up. Okay? That's a little harder to visualize because you can't always just pick up the graph and fold it. But we've got some algebraic tests that can help us with that. But even functions, symmetric with the y-axis, with respect to the y-axis. Odd functions, symmetric with respect to the origin. Neither is just going to be anything in between that doesn't do either of those. Okay, let's look at some functions real quick. We're looking for odd, even, or neither, or neither if you're not from Decatur County. So here's a function. I don't know where the line is that teaches you to say neither instead of neither. It's always been neither. All right, here's our function. We don't want to know is that odd, even, or neither. So we've got an equation, so we're gonna do the algebraic test. If I plug in negative x, what happens when I square negative x? Comes positive. 6 times positive x squared would be 6x squared. So that one stayed the same. What happens when I take a negative x and raise it to the 4th power? Does it stay positive or go back to positive, or does it become negative? It goes back to positive. Negative 3 times positive x to the 4th is negative 3x to the 4th. What does that look like? It's the same as the original, right? So this is an even function. Here's the shortcut. Look at the exponents on the original. What are both of them? What kind of numbers are they? They're even numbers. X squared, x to the 4th, both even. If all the exponents in the problem are even, then it's an even function. That's the shortcut. Mathematically, this is what's happening, but the shortcut is, just look at the exponents. If they're all even, it's an even function. If any of them are not even, then we got problems, okay? Let's look at another example. See if we can kind of utilize that shortcut a little bit. X squared plus 7x plus 12. If I do the actual test, I'm going to show that work. I get x squared. I get a minus 7x, and the 12 doesn't change. Does that match the original? Almost. What changed? The 7x, not everything. So something changed. So that means if it isn't everything, it's a neither. So this one is a neither. Let's look at the exponents on that so that we can maybe use a shortcut instead of having to do that on calculations here. What's the exponent here? Is it odd or even? Even. The exponent here is odd. The constant doesn't have an exponent. Okay? So here we have an even and an odd, so it's a mixed match. Anytime it's mixed, it's even. Okay? If they're all even, it's even. If they're all odd, then what do you guess it is? Odd. For example, negative 8x cubed minus 5x. Okay. If I actually do the math, I'm showing that because the math department is probably listening. When I raise a negative x to the third power, it keeps it negative, and that becomes 8x cubed. Negative 5 times negative x is positive 5x. Everything changed signs. So that's odd. The shortcut is look at the original. The first one, the exponent is a 3. That's an odd number. What's the exponent on plain x here when there's not one written there? It's a 1. 1's an odd number, right? So the exponents on every piece was odd. So that means it's an odd function. Anytime you may have something like this, 7x to the 5th minus 5x to the 3rd plus 2x plus 3. Is that odd, even, or neither? Let's look at the exponents. Odd, odd, odd. Uh-oh. Doesn't have one. So it's mixed in there. That's a neither. Anytime there's a constant, it's neither. Anytime there's a term that does not have a variable, you know automatically that it's neither. If you had something like this, f of x equals negative 4x to the 8th plus 6x to the 4th minus 5x squared. What do we know about that one? Even. 8, 4, 2. They're all even. So it's even. If everybody has an odd exponent, it's odd. If everybody has an even exponent, it's even. If there's anybody that mixes it up, either has an even exponent and then another piece has an odd exponent, or there's a term that doesn't even have a variable, then it's a neither. Okay? Odd, even, or neither. Okay? Graphically, if they give you a graph, think symmetry. If you can fold it across the y-axis and the y-axis only, then and it match up, that's odd. That's even. Origin is odd. So you got to go y-axis and then fold it down across the x-axis. Sorry, my hands aren't flexible enough to do that. So at y-axis and then down. If it matches up then, it's odd because it's symmetric with respect to the origin. Those are tougher to do. Okay, so tougher for that to happen. All right. Let's look at a little sketch of a graph here. I'm just going to sketch a small graph, and I'm going to label some points I'm not going to put tick marks or anything. I'm just going to label some points. And then I'm going to draw a graph. One more point right here in the trough of that loop. Not an example G, we're on F, aren't we? So this is similar to what we did at the beginning of section 2's notes. It's just a different graph, okay? Now, what we're going to look at here are the domain. Let's start with that. What's the domain of that particular graph? What's the lowest x value? -6. What's the highest x value? +6. There's our domain. What's the range? -2, +4. Good job. Now, here's the new things. Where is this graph increasing? Okay, so when we're looking at this, we're looking for where is the graph increasing from left to right. If you're increasing from left to right, what direction should you be going? Up. Okay, so when you read a graph and you're looking for intervals of increasing or decreasing or constant, you're reading it from left to right. So if I start here, left to right, what is this graph doing from -6 to here? It's decreasing. So we're going to go ahead and be, so we're doing all that at once. We're just going to go ahead and list those two. So from -6 all the way to -4, it's decreasing. I'm using parentheses there because, you know, does it start increasing at -4 or does it stop decreasing at -4? There's no real way to tell. So just when you're talking about increasing and decreasing, just always use parentheses. Don't use brackets at all. Okay. From -4 all the way to what is it increasing? All the way up to 0. So it's going up all the way to 0. So there's an increasing interval from -4 to 0. At 0, what does it do? Okay, it stays constant. It's got the same y value from 0 all the way to where? 3. So we have an interval where it's constant, 0 to 3. And then what's happening after 3? It's going down, right? So we're decreasing to 6. So we have another interval here, 3 to 6. Really easy thing, just read it, the graph. Make sure you're reading from left to right when you're doing that. And then you get your intervals of increase, intervals of decrease out of that. Really easy thing. All right. Next thing, local maximum, and local minimum. Local means what? What does local mean? We're talking about parsons. What's local parsons? I'd say somewhere close to you, right? like say Atlanta, Georgia is not local, right? Okay, so we're talking about a local maximum or a local minimum. We're saying within a certain area. And depending on what you're doing, what's local. If I'm looking to buy a hammer, I'm not going to drive all the way to Knoxville to go buy a hammer. I need something more local than that. So I need to say, okay, if I'm looking it up on the internet, that's the best example I'm giving. Is if I'm shopping for something and I need to find something, a particular car part or something like that, I need it to be within driving distance of me. So I can set my parameters when I'm looking for that part to within 50 miles. That gives me some sort of range or interval to look at. Local maximum and local minimums are within a given interval. Okay? An absolute maximum or minimum that's over an entire domain. An absolute maximum or absolute minimum is the maximum is the highest point across the entire domain. Minimum lowest point across the entire domain. Locals they're going to say, okay, look between 2 and 8. What's the local maximum between 2 and 8? So what's the highest point on the graph between those two X values? What's the lowest graph between the lowest point on the graph between those two X values? They're going to give you some sort of interval. Locals are just looking for in a small window. Absolutes, we're looking across the entire domain. What's the highest point for a maximum? What's the lowest point for a minimum? So make sure we're looking at know the difference in those two: local maxes and absolute maxes and mins. Locals and absolute. Absolute means across the whole picture. Locals means within a certain given interval. And it's just like looking at the increasing and decreasing interval. I don't want to do an example of that. Just know the difference in those two. Because if it's local, it's within a small window. Absolute across the whole thing. Okay. All right. I'm going to show you how to do that. Find some locals with a graphing calculator. I'll show you that fairly quickly and getting close to being done today. Just a few more things with the TI-84. Let's say we had this function, f of x is 3x to the third minus 7x plus 1. And I don't even know what letter I looked at it. G. Find local max and min for -2 to 2. Okay. That looks like an ordered pair, but it's an interval. Anytime they're talking about local maxes and mins, and they give you 4 something, that looks like an ordered pair, but it's an interval that we're going to look at. So what we're going to do with the graphing calculator is we're going to graph that equation. 3x to the third. Oops. Back up there. And I forgot what it was. Minus 7x plus 1. Minus 7x plus 1. We graph that. And then it said look in between -2 and +2. Well, I can look there and I can see, okay, where should the local max be between -2 and +2? On top of that little peak right there, right? We got to find that. The local min should be down at the bottom of that little trough. We got to find it. Okay. Calculator has a nice tool to help you find that ordered pair. What you do is you hit second and then the trace button and look at choices 3 and 4. Minimum and maximum. Nice and handy. it'll give you the exact decimal point for that. So I'm going to pick the maximum first. I'm going to pick number 4. And the left bound, I'm just typing in -2. The right bound is the other end of my interval. It was +2. Then it asked me to guess. It actually is important that you move the cursor to guess as to where it's at so that it knows which one you're looking for. Because sometimes there might be more than one local max in between there. But we're going to move that cursor. I'm just going to press the left key until I get close to that peak. Hit enter. And it tells me that the maximum is at this order pair, -0.88, 5.12, around the 2 decimal places. Max at -0.88, 5.12. I'm going to repeat that for the minimum. Second trace, minimum, left bound's -2, right bound's +2. That's the interval they gave me. And then it asked me to guess. I'm just going to move till I get close to that bottom there. Doesn't have to be right on it. Just got to be close. I think that's real close. +0.88, -3.12. Okay. So you can use the technology that we've got to help you find those local maxes and mins. They're going to give you an interval to use. That's your left bound and right bound. Okay. Left bound. That's your right bound. Okay. When you use the graphic calculator, left bound and right bounds off the interval they gave you. Okay. All right. Last couple of things are fairly easy, Algebra 1 kind of stuff, but it may have been a while since you did it. So I'm going to go over it real quick. Average rate of change. College algebra, they like to fancy things up and use some Greek letters and things. And a fancy formula. What that says is delta y. So the Greek letter delta y over delta x. That means changing y over changing x. And then this notation is the y value when x is b minus the y value when x is a divided by the x value b minus the x value a. That's fancy stuff for something you've seen before that we wrote in algebra classes in high school. M equals y2 minus y1 over x2 minus x1. This formula you've seen before, I know. That one over there, maybe not so much. That's more of a college algebra level formula. This is all it means. That's what it is. It's slope. Average rate of change is slope. That's it. Okay? Here's what we do. They're going to get us to find the average rate of change for f of x over 1, 3. And remember, that 1, 3 is an interval. They won't tell you it's an interval, but they mean it's an interval. Okay? We're on. I think that's a G. What do you say? Okay. Here's our f of x. That's our function. They want to know what the average rate of change over this interval is for that function. So to find an average rate of change, that's finding the slope, we've got to have 2 ordered pairs. They give us the x values, 1 and 3. we need the y values to go with those. So we got to plug those in and work them out. So we're going to plug in 1 for x. Work that out. That'd be 2 minus 5 is -3. And then we're going to plug in 3 for x. 2 times 3 squared minus 5 times 3. So 2 times 9 would be 18. 18 minus 15 is 3. So we get this f of 3 is 3, f of 1 is -3. We have 2 ordered pairs. We can take that and find the slope. Remember, slope is take the y values and subtract them. y2 minus y1. Take the x values, x2 minus x1, and subtract them. It doesn't matter which y value you start with. Pick one. I'm going to pick the +3. And then I'm subtracting the y value from the other one, so -3. And then on the bottom, I've just got to keep the x's in the same order. So if this is the y value I started with, the x value I have to start with is this one. 3 minus 1. So that's going to be 6 over 2. 3. That right there is our average rate of change. Just slope. That's all it is. Average rate of change is slope. All right. Last thing is a secant line. It's going to be in the form y equals mx plus b. It's a line that intersects the given function over a given interval as slope that is the average rate of change for that interval. Okay, so the secant line is the equation of a line that's going to intersect our function over a given interval. They're going to tell us what interval to use, and then we're going to take that and find an equation that goes with that. That slope that we find from that interval is the average rate of change, just like what we just did on that previous example. Okay, so let's take a function. Let's say, I don't know what letter we're on. Okay, I. Here's our function, f of x equals, let's do 3x squared minus 2x plus 3 over the interval from -2 to +1. We want to find the equation for the secant line. In geometry class in high school, you probably talked about secant lines, and tangent lines were probably a little bit more common. Tangent lines meaning they only touched in one spot. Secant lines touch in 2 spots. They cross like that. But tangent lines only touch in 1. Secant lines are easier to find than tangent lines. So let's look at finding that. So the first thing we got to do is find the average rate of change over that interval. So what we've got to find is f of -2. So that'd be 3, -2 squared, 2 2 times -2 plus 3. Working that out. 4 times 3 is 12 plus 4 plus 3. So 7 and 12 is 19. So f of -2 is 19. Then I'm going to do the same thing for +1. Three minus 2 plus 3. That'd be 4. So here are our ordered pairs that we're going to use to find the average rate of change, or the slope of our secant line. Average rate of change and slope of the secant line are exactly the same thing. Okay, so to do that, we'll use the slope formula. 19 minus 4 over -2 minus 1. 15 over -3, which is -5. Now, again, secant line is going to be in slope-intercept form. So that's y equals mx plus b. We know this guy is m. So that's -5x plus b. We have 2 ordered pairs that we found. We got to use one of them. It does not matter which one you use. Just don't mix and match. Just pick one. I'm going to pick 1, 4 because it's smaller numbers. It's easier to do. Okay? So I'm going to pick 1, 4 and plug it in here. 4 goes in the place of y. 1 goes in the place of x. And that's going to let me find out what b is. So 4 equals -5 plus b. Add 5. 9. B is 9. So our secant line is y equals -5x plus 9. Y equals -5x plus 9. If we graphed that original equation on the calculator, and I'll do that just to finish this up here, 3x squared minus 2x plus 3. And then I'm going to graph the secant line as well, -5x plus 9. I'm going to graph both of those. There's that red line is the secant line. I'm going to hit zoom 6 to. How's that not good? Window. I'm going to zoom out. That way we can see it covering the. See how that red line hits that graph 2 places? Those 2 places are the ordered pairs we found. That's what a secant line does. It should hit it 2 places. But that's always a checking spot for you. Graph your calculator. Graph the original. Graph what you found was a secant line. If it doesn't hit it twice, then something went wrong. And you know you got to rework there. Okay? So some problems that if you're looking at the textbook to get a little guidance here on page 237 of that book, 1 through 79. Odd. Obviously, you don't need to do all of those. Just pick some that would work for that. Things that you'll see this week. Your Canvas quiz will open up tonight. You'll be able to work that. You'll have 2 weeks because we will not meet next week because it's Labor Day, so no class next week. You'll have until the next class meeting to complete the first Canvas quiz. Remember, you get 2 opportunities. Don't wait till Monday of 2 weeks from now to take both opportunities. Take it the first time, print it out after you get done, and then you can work on that. And then when you go back the second time, you get a better score. I keep the highest one. That's what I do. Okay, keep the highest one. If you got questions, email me, send me a Canvas message on that. I'll send out an announcement about the YouTube videos of the lesson and all that stuff. If you need to rewatch